All right. Let's listen up, turnips. Time to start. Turnips. Listen up, turnips. I thought it was cute. I thought of it last night. Okay. All right. So let's start by revising some Lewis structure stuff. Organic people. All right. My organic people. My science people. We are. So that way the thermal people can hear the notes. All right. So let's do some refresher on Lewis structures. We did a couple for our do now. Lewis structures are a great way for us to communicate what's happening with the molecule. So I first gave you guys ammonia. Now, just to recap what you guys will be doing when you are trying to deal with Lewis structures is you are seeing how many valence electrons they have, and then we're figuring out the bonding that's going to occur in order to make everyone stable at an octet. So nitrogen, its valence electron number is going to be 5 because it's in group 15. So nitrogen has 5 valence electrons. Come on, focus, focus. There we go. There's only one of those atoms, so 5 electrons are coming from the nitrogen. The hydrogen has 1 valence electron, being in group 1. Trying to get this guy to focus. We have 3 atoms of the hydrogen, so we multiply that by 3, giving me a total of 3 there. And so when I add those two numbers together, I have 8 valence electrons that I am working with. Really important that we do this calculation for our Lewis structures, so that way we know exactly how many electrons we are dealing with. I don't want us accidentally creating or destroying matter. Okay? So when it comes to drawing the structure, we need to figure out what the center atom is. Center atom is usually the one that can do the most bonds and is unique. So when I'm looking at nitrogen, nitrogen to fill its octet rule only needs 3 more electrons. Hydrogen, on the other hand, can only have 1 more electron to fill its octet because remember, it's an exception to the rule. It's a very tiny atom, so it only needs 2 electrons. So it makes more sense for nitrogen to be in the middle. And on top of that, it's the only one that we have where we have 3 hydrogens instead. So we'll do nitrogen in the middle. With Lewis structures, we assume that everybody needs to have at least 1 bond to connect all the atoms, so that way my atoms aren't floating around. I have drawn lines. You could have also drawn dots to represent the bonds, because those lines are actually representing 2 electrons in a covalent bond. Both of them are deemed correct. I personally like the lines because when it gets to the shape content that we'll do next week, it helps us then distinguish what is and isn't bonded. Right now, I've used a total of 2, 4, 6 electrons. Out of my 8, I have 2 remaining. When it comes to adding the electrons, we add them from the outside going inwards. The hydrogens are all fine because they only need 2 electrons to be stable, which they do have already. So what that tells me is that the last 2 electrons will go onto nitrogen. So that's what we have for that model there. Cool. Happy campers? Right. Do you want me to go through that same level of detail for explanation for the other 2 molecules, or should I just draw them? Yeah. Go through the same detail? Okay. Next one we have was a dichloromethane. That was CCl2H2. So again, we look at the periodic table, we see what group they're in. Carbon's in group 14, so that's 4 electrons. We only have 1 carbon, so that means 4 electrons from there. Chlorine is in group 17, so that's going to give us 7 valence electrons to work with. We have 2 chlorine atoms, so that gives me 14. And then hydrogen's the last guy that we have. Hydrogen is group 1, and we have 2 of those, so that means we have 2. Again, do the math to figure out how many we have. So that is 18 to 20 electrons. Happy with that? All right. Center atom is going to be carbon. Carbon can do 4 shared electrons. The other guys can only do 1 more electron, plus carbon's the only one. So when it comes to drawing, we will put carbon in the center. We have to assume that there has to be at least 1 bond for everybody, so that way they can be attached. Now, I am not fussed, and the examiners will not be fussed on how you orient the chlorines and the hydrogens. This is one version. If you drew it like this, that would also be accepted. It's still the same molecule. So just keep that in mind as an FYI. You can move those guys around. So long as they are attached to that carbon, you are fine to go. Cool. All right. Right now, I have used 2, 4, 6, 8 of my electrons. So I have 12 left over. So those 12 need to find homes. We are going to go from the outside going inwards to add electrons. The hydrogen in this case don't need any more electrons because they are stable with 2, so I can tick them off. The chlorines, however, only have 2 each, so I need to start putting electrons on them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've used up all 12 of my electrons. Chlorine is stable. It has 8. Chlorine is stable over here. It has 8. And then carbon, when I look at it, has 2, 4, 6, 8. It is also stable. So that molecule is now done. I'm going to put the electrons on this guy too. Questions, concerns, comments? I heard a Klein? Is that a question? No? We're okay? Yeah. You know how you got the 4 sigma and 1? Yep. Yeah, what do you get? I got them from the periodic table. Let me just grab one so I can show you what I mean. Yeah, because you wouldn't have done this. So you didn't take chemistry last year. So, periodic table, as we were talking about in Monday's lesson, which I don't know if you were here for. Remember now. The periodic table has multiple trends. One of the trends we are looking at in this case is that the columns tell me valence shell electrons. So how many electrons are in that outermost shell? If you are in group 1, you have 1 valence electron. If you're in group 2, you have 2 valence electrons. If you're in group 3, you have 3 valence electrons. Sorry, group 13. 14 would be 4, 15, 5, 16, 6, 17, 7, 18, 8. So what I do is I look for the element on the periodic table. Here's carbon. It's going to have 4. I look for chlorine. It's in 17. It has 7. So that's where I'm pulling these numbers from. Make sense? And you will be given a periodic table on the exam. All right, last example. Okay. Last one we have to deal with is carbon dioxide, CO2. So carbon has 4. There's only 1 there. Oxygen, when I look at it, let me show you what I mean, Isaiah. Group 16, 6 valence electrons. So that's how I'm getting these numbers. And then I'm multiplying it by 2 because I see that there's 2 oxygen atoms. So that would be 12. Oopsie, I'm going to write it over here. Total then that I'm working with is 16. And again, we want to specify this because we are not creating or destroying matter. All right. We assume carbon's going to go in the center because it can do the most bonds. We have to assume that oxygen needs to be attached at least once, so that way the atoms don't flow away. Right now, I've used 2, 4 of my electrons, so I'm down to 12. We okay with that? Okay. Now I go outside going in, so I'm going to start with the oxygens. 1, 2, 3, 4, 5, 6. That one's stable now. 1, 2, 3, 4, 5, 6. That one's stable now. I have a problem though. I look at carbon here, and carbon only has 2, 4. It has not met the octet rule. It needs to be at 8. So what I'm going to do is I am going to move some of these electrons from the oxygen and now going to put them into a bond with carbon. So the oxygen still has its 2, 4, 6, 8, but now carbon has 2, 4, 6. And then same thing, I can remove those 2 oxygens. Oh, I know. And draw that. So if I was to tidy this up to draw it, I would show it as C double bond O, C double bond O, dot, 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 dot. Again, they're not going to be fussed where you put your electrons. So if you want to do like that, that's also deemed correct. So I don't want you guys sweating over the small details like that. Cool. Questions, concerns, comments? Keep going. All right. I figured I might as well give you guys the stuff for this year and not just stop at this point. So that way you guys can actually do the whole kind of list of work. Okay. So if you guys remember, we talked about some exceptions to the rules. So most elements will want to get 8. So most elements are stable with 8 electrons. We call that the octet rule. But there are a few exceptions of certain elements that will be stable with different numbers. The first one we've already talked about is hydrogen. Hydrogen is stable with 2. So when you guys are doing your electron configurations, you only need to make sure that the hydrogen has 2. The next exception is beryllium. Beryllium will be stable with 4. And the last one we talked about last year was boron. It will be stable with 6. So basically these guys, you don't fill to the octet rule, you just fill to this number. They are small enough atoms that they can be stable with these numbers instead. Do you want to see an example of an element like that, or are you okay? Yes, please. Okay. So for example, if I was dealing with BH3, so similar to the ammonia, NH4. When I look for boron in the periodic table, boron is 3. And then there's only 1. Hydrogen is 1. We have 3. So that's 6 total. Yeah. I would put boron in the center. I would assume everyone has a single bond. And in fact, I'm already done. Because if I look, 2, 4, 6, I've used up all my electrons. Hydrogen stable, hydrogen stable, hydrogen stable, because all of those have 2 electrons. And the boron is stable because it has the 6. So it's done. So those are the exceptions. Why? Because boron is a small element, and so it can be stable with 6 electrons. It doesn't need 8. And that's done. Okay? Right. There is another exception to the rule, and this is now new for year 13, and that is the extended octet. So what this means is that these elements can have more than 8 electrons and be stable. So these guys can have anywhere between 8 to 12, and they will be fine. 8 to 12 electrons. This occurs for any element that is past silicon. So basically phosphorus and above can do this. Nope, silicon, Si. So that would be phosphorus and above. So including phosphorus, so phosphorus, sulfur, chlorine, all those guys. The reason has to do with the fact that they can move these additional electrons into their vacant D shell. So they're large enough atoms that they can do that, which is really useful. And I'll give you guys some examples so you know what they look like. All right, keep going. Hold on. Write that down. I should also add, knowing these Lewis structures is really important, because if you misdraw your Lewis structure, depending on the structure of the question, it could snowball and affect your shape justification, just like last year. So take your time and get the Lewis structures correct, so you don't have a snowball happening. Are you ready to see this in action? Oh, Brooklyn says no. It's okay. Be nice. Monica Michelle, you ready? Okay. Start writing down the next example. We're looking at phosphorus, and with 5 chlorines attached to it, PCl5. All right, let's do some math. So phosphorus is in group 15, 5 electrons there that I'm working with, only 1 atom of that. So 5 electrons are being contributed by that. Chlorine is in group 17, 7 valence electrons being contributed there. You have 5 atoms of that, so that is 35. Everybody happy with me on that? Okay. Add that up, we have a total of 40 electrons. All right, which guy do you think is going to be in the middle? Phosphorus. All right, and then I need to assume everybody has 1 bond. So 1, 2, 3, 4, 5. Whoa. Haven't seen that before. I'm allowed to do that though, because what did we say? Anything beyond silicon can have more than 8 bonds. Sorry, more than 8 electrons. Anywhere between 8 and 12 will still work for phosphorus. So phosphorus is stable in lots of different conditions. That's why it's such a good building atom. So 2, 4, 6, 8, 10 is what has been used. Yep. So I'm now down to 30. Okay? All right. Let's start putting down our 30 atoms going outside in, sorry, electrons going outside in, and then anything left over goes on phosphorus. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. That guy's done. Make sure you double check your electron count, because if you get this wrong, it's going to snowball and affect the next question we talk about. because you need to use that Lewis structure to determine that shape. I'll give you guys a few more examples, just because I think since it's the first time you guys are seeing this, it'd be good. Or do you guys want to try this one, and then you can check your answer? How about that? Do you guys want to give this one a go? And then check your answer with me? Yeah. Where is that fx? Not fx. xe. xe is 18. So it is 8. xe is 8. I know, but we're dealing with bigger atoms. And then fluorine is 7. You have 4 of them. So that would be 8, and then 21, 28, right? So you are dealing with 36 atoms? Sorry, 36 electrons? All right, figure it out. Okay, here's the answer for this guy here. Now, you would have gotten to this point, and you would have 32 electrons, and so the remaining 4 go on the center atom. True? All right. Do you want another one? Okay. I want you to do PCl3O. Do you want me to find numbers for you? No? You can find them yourself? You should try to find them yourself. All right, go try that one. Okay. Phosphorus has 5, only 1, so that's 5. Chlorine has 7, there's 3, so that's 21. Oxygen, 6, only 1, so that's 6. That is 26 plus 6 is 32. Is that what people got? Okay. Phosphorus will be our center atom because it is able to have the most bonds to it. Oxygen, chlorine, chlorine, chlorine. And we have 2, 4, 6, 8 that we have used. So 32 minus 8. Now this is where my mental math stops working. That's 24 left over. All right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So that is the answer that I have from there. I do want you guys to kind of keep in mind, so phosphorus is stable right now. It has 8 electrons. Do be mindful that some of these molecules, especially with these larger molecules, is that they can have multiple different setups that are all correct. If you had Googled this molecule, you would actually often find it like this. That is a common variation of the Lewis structure, and it still does work. What has happened is one of these lone pairs of electrons has gone in to make a double bond with the phosphorus. Both of these are going to be marked as correct answers, though. So don't fret. I just wanted to show you in case things do pop up when you're Googling and you're like, why is that answer different from my answer? In some cases, it's just a matter of they're moving some electrons around. Are you okay? All right. Last example, and this one I kind of want to walk you guys through, is what happens if you have an ion. So they might ask you a polyatomic ion for the Lewis structures this year. And in fact, I think it's pretty much guaranteed, such as Pl6, and there is a negative sign attached to it. So here are some things I want you guys to keep in mind. It's pretty logical. You are still doing the same steps as before. So phosphorus, there are 5 electrons. Chlorine, there are 7. Multiply it by the number of elements that you have there. So that's 5. 7 times 6 is 42. Now, the thing you have to remember whenever you are dealing with ions is that you need to factor in the loss or gain of electrons based off of that ion. So since this charge here is -1, that means that it has gained an electron. So when I do this math, I need to add 1 more electron to it from the charge. If you had a positive ion, you would be subtracting an electron away because they would have lost an electron. So just kind of keep that in mind. Do you want me to write that down? Yeah? Okay. So negative ions, you are adding the charge, or the value of the charge, to the valence electrons. Positive ions, you are subtracting. And I'm just going to do that. Whatever the charge is. So in this case, what I would be working with is 6 plus 42. You are dealing with 50 electrons. Same method as you would before. Phosphorus is your center atom. This guy is showing that I can hold up to 12. Put all my chlorines around it. And then drop your electrons on your chlorines. And then what I would do is I would double check your electron count. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 50. Yeah? Yeah. Oh, so 5 from the phosphorus, 7 from the chlorine, and we have 6 of them. That's the 42. And I've added an extra electron because this is an ion. Is it 48? Did I do my math right? You're right, 48, sorry. Thank you. So what is that? 2, 4, 6, 8. 8 times 6 is 48. Yeah, sorry. Good checking. All right. Last step then with these ions is you need to put them into square brackets when we're drawing their Lewis structures, and then put the charge of that polyatomic ion on the outside. So any ions, you got to do that. If it's not an ion, you don't have to worry about doing that. All right, let me find your checklist for thermo. Left in the other room. Me? I just want to show you guys how this breaks down point-wise. So, just kind of recap the work that we did today and how it's going to play out on the exam. We looked at number 6, drawing those Lewis structures. On the back, let's see where those Lewis structures came in on a question. Oh, we've done all these. I did not put the Lewis structures on here for some reason. Oh, here we go. On the bottom, as an achieved, I can draw the correct shape and Lewis diagram for complex molecules. So we're looking at that one there. This will lead into the merit and excellence level answers with the justification of shape and polarity. But this is the first step. Looking at the audit, so you guys can kind of see what we've done this one too. I forgot to take that off the other day. All right. We've talked about the Lewis diagram of a molecule. So that comes up quite frequently, if you guys can see, 2020, 2018, 2016, 2015. We'll do shapes tomorrow. Lewis diagram of ions, again, it does come up. That one they did in 2020, 2016, and 2014. I would say it's very likely they're going to ask you to draw a Lewis diagram. All right. We'll talk about the shapes in our next lesson. But again, you can see that the shapes of the molecules come up again pretty regularly. Cool. All right. So that's all the content for today.